All right, we are now recording. Let's get the screen set up, and let me go over my major announcements. It's not huge, but it just affects mostly office hours. Okay, and this affected yesterday as well. I'm taking my physical science class on a field trip to Sanford Planetarium, on Sanford University campus today, this afternoon. And how that messed me up yesterday, I had all the paperwork to run for that, so basically I had no office hours yesterday either because I had to run to the Birmingham campus and get all the signatures and everything like that signed. And then I spent the rest of the afternoon there. What that led to, I didn't have time to organize today. And then this morning when I was getting my stuff, I said, "Where's my quiz?" I said, I forgot to drop it off at the copy room. So that's what I had to do on my way up. And that's why I don't have the quiz here, but it's probably copied now, and Nathan was asking for it. So that was why I was late getting here today. I had to take that by the copy room this morning. Okay. Now, how does that affect today? That's all old history, right? Well, as soon as my trig class is over with at 10:45, I have to book it to the Birmingham campus so I can pick up the van and get it back here so I'll have it ready when we leave. So basically my office hours today are supposed to be 10:45 to 12:30. You can just about bet that 10:45 to 11:15 on the most liberal estimation, I'll be on the way there, whatever time it takes me to get it, and then driving back, that's another 30 minutes. So I'm almost certain I won't be back here before 11:45, and it'll probably be closer to 12 o'clock. So now my office hours are something between 11:45 and 12 and 12:30, because at 12:30 we're leaving to go to the planetarium. So my office hours are almost non-existent today. Could have as much as 30 to 45 minutes. I doubt the 45, but I guess it could happen. So anyway, very limited office hours today. And from 12:30, we'll be going to Sanford. Probably get back here 3 o'clock or so. But then that's about the time my lab is supposed to be, so we'll be having class then from 3 to 5. So I will be available after 5 o'clock. I do have to take the van back to the Birmingham campus after 5, but I can do that anytime after 5. So if you do need to see me and can't catch me right around 12 to 12:30ish, then after 5 I should be in the office. But if you don't catch me right after 5, I'll be on my way back to Birmingham to return the van. So it's kind of crazy. Okay, but tomorrow office hours are as normal, 7:45 to 1, as far as I know. We had a meeting last Friday, so I hope not to have a meeting this Friday. I've got plenty to do. I don't really care for the possibility of a meeting. Any questions on anything we've covered so far? All right. We're starting today then in 1.6. Chapter 1, of course, is functions and their graphs. Please note, this book loves the graphs, okay? So, and a lot of this section is do it. A library of parent functions. Interpret that. A library of the graphs of parent functions too. I mean, no, we'll be talking about their nature, but also graphing. We'll identify and graph linear and squaring functions. That will be the first part of this section. We'll identify and graph cubic, square root, and reciprocal functions. That's the second part of the section. We'll identify and graph step and other piecewise defined functions, and then we'll recognize graphs of parent functions, sort of the summary of all of those. Okay? Now, let's start with linear and squaring functions. This is on, of course, page 60, if you've got the text there. Okay. One of the goals in this text, if you haven't noticed so far, is to enable you to recognize the basic shapes of the graphs of different types of functions. Big on graphing. For instance, you know that the graph of a linear function is what? A straight line. That's why they call it a linear function because it graphs into a line. This is the expression of that. Does that look familiar? Alpha of x is equal to ax plus b. How so? What does that look like? Okay. Think even simpler than that. What is F? Okay. Y is equal to mx plus b. What does that mean? B is the y-intercept, and A or M is the slope. There it is. That is your slope function. Slope formula, okay? Except written in function notation. Right there. F of x equals ax plus b with the line with M is A, and the y-intercept is 0b. By the way, y-intercept, I'll let you get away with b. Y-intercept is a point. So it's 0b, okay? Because you said x equals 0, y is equal to b, all right? So let's see the point 0b. All right. Here are some characteristics of a linear function. The graph of a linear function has the following characteristics. The domain of the function is all real numbers, okay? There's only one line that you can draw that doesn't have a domain of all real numbers. And what would that be? A vertical line. Okay, so we messed up here. That function wouldn't be, except that is a vertical line a function. No, it sort of fails the vertical line test pretty miserably on that line that has an infinite number of points, okay? So no, a vertical line does not represent a function, okay? So therefore, that's absolutely correct. Every other line, no matter how steep or shallow or anything, goes in both directions, all real numbers, okay? Now, when m is not equal to 0, we'll start there. The range of the function is what? All real numbers, okay? Now, picture this. What is, when m is equal to 0, what kind of line is that? That's a horizontal line. There the range is whatever that value was, b, okay? That's got to be it. That's all you got, okay? But any tilt at all, slightly positive, slightly negative, whatever, the range is going to be all real numbers, okay? So, as long as m's not 0, the range of the function is also set of the real numbers. Now, you know what the y-intercept is, don't you? 0b, okay? Now, the x-intercept, okay, it's just a little, I wouldn't memorize this. If you ever need to know the x-intercept, okay, give me again the function, function or the equation of a linear function. F of x equal ax plus b, okay? Now, whereas the y-intercept is where x is equal to 0, y is equal to b, that's pretty simple, right? What would the x-intercept be? Where y is equal to 0. Where's your y there? F of x. So when that's equal to 0, that says that ax plus b is equal to 0, right? Okay? Solve for x, and you'll find your x-intercept. What would you do? Subtract b from both sides, and that gives you ax is equal to negative b, and then you would divide both sides by a, okay? And that gives you x equal minus b over, minus b over a. And that's why they say this, except a, they're now using for m. I mean, a is m, remember, that's your slope. Okay? So there's your x-intercept. Do I go around thinking that every time I want to do it? No, I just calculate and see what it is. Set y equals 0 and solve for x. I don't memorize the formula minus b over m. If you want to, you can. There's no problem with doing so. Justin's here. All right, anyone else come in since the call roll? All right. Now, other features are characteristics of linear functions. When the slope is positive, what kind of function is it? Increasing function. Okay? And m greater than 0 or a greater than 0, either way there. And when m is less than 0, it's a decreasing function. And if m is equal to 0, constant function. Okay, so we got our increasing, decreasing constant there. Very good. Any other characteristics? Well, they don't list any, so we'll move on from there. Let's do example 1. Write the linear function f for which f of 1 is equal to 3 and f of 4 is equal to 0. What are we going to need to know to write the linear function? Give me the standard form for a linear function. F of x equal ax plus b. Now, can you tell me what either the a or b stands for? A is the coefficient of x. What else do we know about it? It's also the slope. Now, does anything they tell us there give us a slope? Doesn't look like it, does it? Except, tell me what these things stand for. What does 1 stand for here? No, 1. X, that's an x value. And the f of 1 would then be a y value. So there's the xy ordered pair, right? And guess what? Another xy ordered pair. Okay? So if you knew we had 2 points, what were they? 1, 3, and 4, 0, if I could write. Now, I said if I were to say to you, can you give me the slope between those 2 points? You would say, sure we can, right? How do you get that? What is the slope between 2 points? Say again? Ha, okay. M is equal to y2 minus y1, go on, over x2 minus x1. What in the world does that mean anyway? That's the slope formula. But what in the world is a y1, y2, x2, x1? What is that? Those are coordinates of the points. Now, it doesn't matter which one you say is 1 and which is 2, but once you make that first choice of what y2 is, everything else is fixed. You can't be fiddling them around anymore. So what you want to use is a y2. 3, why not? Okay? So we'll choose y2 equal 3. The others have no choice at all. You've got it fixed. So what would you put here? 3 minus 0 over 1 minus 4. What's that equal to? Okay, negative 1. 3 divided by negative 3, that's a negative 1. There's your slope. Your a is equal to negative 1. So m is equal to negative 1. That's also your a. A is your m. Okay, we got the a. If we can fill that in right now if you wanted to, we will. But we still don't know the b. How can we get the b? You have 2 choices. You may have more than that, but I can think of 2 easily. What does this stand for? Y. Okay, so let's say that as a y. Y is equal to, what was our a? Negative 1, so negative x plus b. Okay? That's the beginning of the equation of the line. We just don't know the b. But guess what? We know 2 xy pairs, don't we? You can pick either one of those, plug them in for x and y here, and calculate the b. Right? Which one you want to pick? The first pair, and what does that give you? 3 is equal to negative 1 plus b. Can you solve for b? Add 1 to both sides, and that gives you 4 is equal to b. Guess what? We have our equation, the linear function for which those 2 points fits. F of x is equal to minus x plus 4. Now, if you don't believe me, okay, let's just see if both of these fit. When you put in a 1 for x, what do you get? Negative 1 plus 4, 3. Very good. When you put in a 4 for x, negative 4 plus 4, 0. Yes, it does work. Okay. So, we found that linear function. Now, we could, if we wanted to, graph it. I have a feeling they will graph it. So, I'm going to let them graph it. Okay? Let's, y'all want to just for fun. Say again? Let's go on and graph it. We don't want to count on them. Okay. Here's our coordinate system. Okay. 1, 2, 3, 4, 5, 6, 7. Negative 1, 2, 3, 4, 5, 6, 7. Positive 1, 2, 3, 4, 5. Negative 1, 2, 3. Okay. Something like that. They're not very evenly spaced, but they're sort of there. Let's first plot our 2 points. How would I get that first one? Say again? Okay, where did you get a 0, 4? Okay. Okay, got it. Okay, his y-intercept is the point 0, 4. Okay, didn't think about that, but you're absolutely right. 0, 4, you start at the origin, and since you go left or right with x, you stay on the y-axis and go up 4. Okay, just don't say yours. Okay. I was thinking these 2 points. Okay? How do we plot those? Say again? Okay, over. What does that mean? All right. Okay, right 1. Up 3. Very good. And what's the other one? Right 4, and don't go up or down at all. It looks like the beginning of a line. Well, guess what? We can also use the slope here and see if it's right. The slope is a minus 1, remember, right over here. What does that tell us? You go down 1, right 1, 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 down 1, right 1. Or you could have gone up 1, left 1. That's also a minus 1. Up 1, left 1, up 1, left. Yeah, you get the general idea. Not a very pretty straight line, but you got it. Make sense? Yeah. The negative x plus 4? Is that what you said? Okay. We started with this. F of x equals ax plus b. We know that's the standard equation, or, function expression for a linear function. That's a linear function. F of x equals ax plus b. Now, what makes that a linear function, by the way? I should have said that earlier. Yes, the x is only to the first power. No higher powers, no fractional powers, no lower powers, no any kind of powers except 1. Okay? That's what makes it a linear function. Okay? Now, the first thing we did was using those 2 points, found the slope, and the slope is the a. So that's where the minus 1 came from. And it came straight up there too, right? Then we plugged in one of those. We could have plugged in the other one. Let's just do it real quickly. Let's plug in 4, 0. Put a 4 here and a 0 there. 0 is equal to minus 4 plus what? B, which is 0 is equal to minus 4 plus, how do you get 0 out of minus 4? Add 4 to it, right? So B is 4. Yeah, we found that again. So our y-intercept, sure enough, is the point 0, 4. Okay? So then we plug the 4 in here. So instead of y, we go back to f of x is equal to minus x plus 4. Okay? See? Okay. Yes? Absolutely. That's exactly what we did. If you think about it, what is rise but change of your values on the y-axis, and run is change of values on the x-axis. So that's exactly what we did, but that's the way I like to remember it, rise over run. Exactly. How much is it going up? And so what you do, change of y over, that's the y, that's the rise, change of x is the run. That's exactly what we did. Right? So yeah, all these things work together for those who know. Okay. All right. Good questions, by the way. Any others? Okay. Let's see how they did it. They couldn't have done it as well as we did. Oh, wait, that's not what I do. I want to go down here and erase all this. Everybody got it? Okay. So, let's see how they solve it. First, to find the equation of a line that passes through 2 points, first find the slope. That's exactly what you decided, and they use the same formula. Y is equal to y2 minus y1. Rise over run. Change of y over change of x. Exactly. Okay? And they plugged in, and guess what? They used it differently. Oh, they're going to get a different answer, aren't they? No, they're not. If you do, this is your y2. That fixes everything else. That makes this your y1. So 0 minus 3 divided by, you have to use this as your x1 then, 4 minus 1. And that would be a minus 3 over positive 3, which is also negative 1. So it doesn't matter which one you choose as 1 and 2. Once you choose it, don't cross them up anymore. Make sure you keep your coordinates in line. Okay. So you get slope of negative 3 over 3, which is negative 1. The way we did it was 3 over negative 3. Still negative 1. No change. Okay. Now, what they did next, different from what we did, and I used to do it this way, but I found it was a little more work. And being lazy like I am, I went for the other, but this works just as well. Did y'all all remember the point slope formula? Of course you did, okay? And you could have plugged that in too. Y minus y1 is equal to m times x minus x1. Okay? Sure y'all remember that, didn't you? Yes, good. Y'all paid attention in earlier classes, okay? Now, guess what? Is there anything different here about what we just did? If you think about it, what happens if you divided this over here? You have the slope formula. The only difference is you have y's and x's rather than y2 and x2. So guess what? If you know the slope formula, you know the point slope formula. Okay? Same thing, just take off the 2's. Okay? Now, you can use either one of the points. Don't have to use the same one you used as x1 and y1 before, but you can. Doesn't matter. So what you do is just plug one of those in. And that's sort of what we did before, but we just did it a little differently. So I guess they chose the 3, 1, I'm sorry, the 1, 3 as their point 1. Okay? So that's y minus 3 is equal, we already knew the slope was minus 1 times x minus 1. Okay? So pick one of those points, x1, y1, whichever you choose, plug those in. Now, what we'll do is try to solve that. Okay? Where would you go from here? I'm going to let you do it. Y minus 3 is equal to negative x plus 1. Excellent. Now what? Add 3 to both sides. And what do you have? Y is equal to, that adds a 0, negative x plus 4. And what is your y? Oh boy, I didn't expect any hesitation there. F of x. Y is always f of x equal minus x plus 4. There, we got it another way. My word. We can't get away from this, can we? That's the answer. You could have plugged in the other point, still giving you the right answer. Okay? So, let me erase this. I hate for them to do the work and you not be able to figure out what's going on. Next thing they do, see, they just jump to the answer. They didn't show how they got it. Sure enough, y is equal to minus x plus 1, and now the y is f of x. I mean, minus x plus 4. Okay. Any questions? Lots of ways to get there as long as all the steps are right. Okay, that's the key. So you found says find the function expression for that. There it is. And then I told you they'd graph it. And they probably did, like y'all did. They chose the y-intercept here. We calculated that, 0, 4. Here was the 1, 3. Here was the 4, 0. And there's the line, slope -1, down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1. Or up 1, left 1, up 1, yeah, you got it. That's your equation of the line. That is your graph of the line. Okay. What's its domain? All real numbers. What's its range? All real numbers. What's its x-intercept? 0, 4. X-intercept 4, 0. And what's its y-intercept? 0, 4. Excellent. Okay. Any questions on that? All right. There are two special types of linear functions that we'll talk about. The first of these is the constant function. We've really already knocked on it a little bit, whether you realize it or not. The constant function has the form alpha of x. It's a constant. Okay, that's why they call it constant function. Now, what can you tell me about that, especially thinking in terms of linear functions? What are you not seeing there? You're not seeing an x. So that means it doesn't matter what x you put in, the y is always a constant. Give me a constant. Name any constant in the world. 5? Is that what you said? So that means alpha 1 is 5, alpha 0 is 5, alpha 17 is 5, alpha negative 3 is 5. Any number you put in there is 5. So guess what? That'll be right up here. It's always 5. No matter what x you put in, the y is always 5. Okay? They chose 1.2 or something like that. There it is. Always 1.2. That's your constant function. Now, since you don't see an x, what must be the coefficient of that x? 0. Okay? Because you can put in any value for x, but since you don't see it, the coefficient must be 0. Coefficient stands for what? The what? The number in front of, but in this equation, it stands for the slope. And that means the slope is 0. What's the slope of that line? 0. It's not going up, it's not going down, it has a 0 slope. Okay? Makes sense, doesn't it? All tied together. Now, what's the domain of that function? All real numbers. What's the range of the function? C. That means yes in Spanish. No. C. That's it. That's the only value you have for your y. Not 0, not 1, not 2, C, whatever C is. The one you gave me would have been 5, okay? Yeah, that's, you only have one value in the range. Nothing else, none of these other places. Remember, if you shine your light down here, the only dark place is at one point, x equals C. I mean, y is equal C, okay? The graph is a horizontal line shown here. Now, the second of these, this should be another paragraph, okay? Forget this line here. It's going to be, should be on the next slide. Any questions about the constant function? Okay, the second of these is called the identity function. Anyone want to make a guess what that one would be? Not a vertical line. That wouldn't be a function. So we don't do that. The identity function is alpha of x. Did they have that on the last slide? Oh, yeah, they did. I'm sorry. Okay. The identity function is alpha of x is equal to x. What does that mean? What does alpha of x mean? Y. Y is equal to x. So if you know x, you know y because they're the same values. That's why they call it identity function. They are identically the same. So give me a few points on it before we go to the next slide. Give me an x. 1. What would y be? 1. Right there. Next. 2. What would y be? Right there. Next. 3. 3. Give me an easier one. 0. 0. Right there. Give me a negative. Negative 1. Negative 1. Down here. There it is. That's that diagonal line, what they call the main diagonal. That's your identity function. Okay? There it is. What's the domain of that? All real numbers. What's the range of that? All real numbers. Very good. Okay? What's the slope of that? 1. Exactly. Go back to the formula. What's your coefficient? 1. So the slope is 1. What's your x-intercept? Y-intercept. Same thing. You see a y-intercept? Alpha of x equals mx plus b. What's your y-intercept? 0, 0. Exactly. So therefore, what's your x-intercept? 0, 0. It's the only place it crosses both. So it crosses at the origin. X-intercept and y-intercept, they're the same. Okay? A line for which x coordinate equals the corresponding y coordinate, that gives you your main diagonal. This is also a diagonal, but that's not the main diagonal. This is the negative. This would be y is equal to negative x. Okay? Don't worry about that one. Alpha of x equals negative x. This is your main diagonal of the identity function. Was there a question? Okay. Any questions on that? Oh, increasing, decreasing. Increasing. Why? Because the slope is positive. It's a plus 1. So it's a positive. Okay? All right. We beat it to death? All right. Let's move on then. The next type we're going to hit is called the squaring function. Clever name. Because alpha of x is x squared. Okay, you just take whatever the input is and square it. Now, I don't really like this expression. I know what they're talking about. They say it's a U-shaped curve. It breaks me a little bit because a U, as you look here, goes straight up. This curve doesn't go straight up. What they're talking about, what it does at the bottom, it's rounded. Okay, that's why they call it a U-shape. Doesn't go straight up there. Now, what do you reckon the domain of this would be? Okay, let's just take a look at it. What is that going to give you? Have y'all ever graphed one that looked like that? That's going to give you a parabola. What's the domain of a parabola? All real numbers. What's the range of that parabola? Say again? Okay, it certainly does. You know if that tells you which way it's facing? Up. Okay, now by facing up means it's curving up. It's cupping upward. Okay? So it's holding water. Okay? That's this one. So therefore, what is its range? Okay, and what's the lowest point on that? 0. So then the range of this would be? Yeah, from y0 to positive infinity. You're absolutely right. Counting the 0, including the 0. That's a bracket around that 0. Okay? Does it have an x-intercept? A y-intercept? Say again? 0, 0. So if it's 0, 0, that's x and a y-intercept. Okay? Because it goes through 0, 0. Okay. Is it increasing or decreasing? Say again? But, yeah. Either or, both. Okay. Which is it where? Yeah, decreasing from negative infinity down to 0, and then increasing from 0 to positive infinity. You got it right. Those are the values for x, okay? And we came to the range, set of all non-negative real numbers. That's the other way to say it. Oh, we didn't talk about even and odd. Ooh, shame on us. Okay, let's go back. Is this function, the constant function, even or odd? It's even, because whatever's happening on the left is happening on the right. Same values. How about your identity function? Odd, because whatever's happening on the left is the opposite of what is happening on the right. Okay, you're right. These are both polynomial functions, remember. What's the exponent for this term? X to the 0th, which is 1. Anything to the 0th power is 1. So this is c times x to the 0th. X to the 0th 1, that's just c. So 0 is even. Put your exponent here. 1, what's that? Odd. That's sure enough an odd function. Okay. And this one is even. 2 reasons. What is happening on the left is the same on the right. The other reason, the only exponent you have is 2, and that's even function. We've already hit the, has an intercept. They don't even specify. It's the x-intercept, it's also the y-intercept. Okay, at 0, 0. All right, here's a picture of it. Oh, yeah, we already talked about increasing, decreasing. Oh, we didn't say this. Where is that symmetric? Symmetric about the y-axis, which is the same thing as saying it's an even function. That's what it means to be even, symmetric about the y function, of the y-axis. Okay. Now, here's another new one here. Okay? Oh, it's not new. We talked about it in the first and second section. This has a, what is this point here called? Relative minimum in this case. Later, we're going to give it another name. You want to know it? Second? Oh, no, this one can't be a relative maximum when it goes like that. Second? It happens to be an absolute minimum, too. But with not minimum and maximum in it, relative or absolute in it, there is another name. We haven't hit it yet. Just wondered if you all run into it before. Vertex. It's also called the vertex, where it changes direction. Okay? Another name for it. Minimum, maximum, vertex. Well, not all things will be that way, but for parabola, it is that way. And this is the graph of it. And that's how the squaring function always looks. Now, you can do other things to it. We'll talk about that in the next section. We can translate it, and we can stretch it and shrink it, and later we'll add more terms to it, and that does all sorts of weird things to it. But this is what they call the parent function, the simplest form of the squaring function. Okay. Let's move on to the cubic, square root, and reciprocal functions. We'll start with the cubic. Now, starting with cubic. Cubic function is like the squaring function, f of x equals x squared. This is f of x equals x cubed. Now, does anyone have a clue what that's look like? Say again? Okay. Let's give me some values. Give me an x. 1. What would the f be then? 1. That's sort of familiar. Give me another x. 2. Say again? 8. So that's a little different from the squaring function. The squaring function, 0, 0, 1, 1, but 2 is 4. 0, 0, 1, 1, but 2 is 8. So it's going up a lot more quickly. Not going up more quickly between 0 and 1, still sort of the same there, but it's going up much more quickly from there on. Okay? How about on the negative side? What do you mean, same thing? It's going down. Okay? Whereas the squaring function went up, this one goes down. You cube a negative number, you're going to get a negative number. Right? Because it uses a negative factor 3 times. If that's an odd number, it's going to be negative. Okay? So it's going down. Okay? And it goes through -1, -1. Then -2 is -8. So it's going down quite quickly. Okay? We've just got a good feel for it. What's the domain of that function? All real numbers. What's the range of that function? All real numbers. The squaring function, remember, wasn't. Squaring function only goes one direction. Cubic function goes both directions. Okay? What? Even or odd? Why? 3 is odd. That's cheating. Okay, but you did it. Okay, that's all right. But also the main reason, whatever it's sitting on the left is the opposite of going on the right. Okay? So, now, what's another phrase we can say here? If the function is odd, it's symmetric about the what? Origin, exactly. If it's even, it's symmetric about the y-axis. If it's odd, it's symmetric about the origin. That will be on page 2. Does it have any intercepts? 0, 0. But the x and y intercept is 0, 0. Okay? Oh, how about increasing, decreasing? Where? Everywhere! Okay? Now, you might say, oh, wait, it may not be increasing right near the origin. Is it? Let's see. Well, we see it's obviously increasing from negative infinity to 0. I just can't tell what it's doing here. So what I'll do is pick me a point very close to 0, but not quite. See if it might be constant there. Give me a number really, really close to 0 on the negative side. 0.01. Okay, let's cube that. 5 zeros and a 1. Guess what? It's still negative. Not very much negative. Awfully close to 0, but it's still negative. And if you go to the same thing on the right, awfully close to 0, but ever so slightly positive. So that's not completely flat there. It's almost flat. It is still increasing. Just very slow. But then it picks up and goes real fast. Okay? So it's increasing everywhere. Symmetric with respect to origin, that's the same thing as saying it's in what kind of function? Odd function. Very good. There's your cubic function. Now the cubic function, other cubic functions that we'll run into, once you start adding more terms here, okay, what you do there, and I want you to sort of use your imagination. What does this look like it's going to? Looks like it's going to approach a relative maximum, doesn't it? But it doesn't. It keeps going up. But over here, it looks like this is coming from a relative minimum. So what happens with other cubic functions, you actually get those. So this is going to be what I think of my picture of a cubic function looking like. But this is the parent function, the actual cubic function, not with any other terms in it. Okay? So there's your cubic function. All right? Let's move on to square root function. F of x equals square root of x. What's its domain? Okay. It's all non-negative real numbers. Why? You can't take the square root of a negative number, so it's got to be non-negative real numbers. 0 will work. Square root of 0 is 0. Nothing to the left of 0. Not even slightly to the left of 0 would work. Okay? What's the range? Yes, all non-negative real numbers on y. And the reason for that, when you write it like this, that is understood to be the principal square root. If you don't see a sign in front of it, that's the principal, meaning principal key positive square root. If you had a minus in front of it, that'd be the negative square root. We don't. That's the principal. So that's going to be all non-negative numbers as well. Is it increasing or decreasing? Increasing. You put a bigger number in there, the square root, so it's not going to be as much bigger, it'll still be bigger. Okay? Even odd. Neither. Because you can't ever go to the left. Remember the test is put a minus x in there. You can't put a negative value in there. So this is a neither function. I don't mention that here, but it is. Does it have an intercept? Yeah, 0, 0 is the one and only intercept. That's absolutely x-intercept and y-intercept. Okay, anything else? Let's see. Oh, yeah. We talked about increasing everywhere from 0 to positive infinity. That's good. Now, just wanted to point this out to you. It's just a little thing, and it's not a big deal. But just to let you know, if you are saying the domain is a set of all non-negative real numbers, that's saying it in words, say that in interval notation. What would be the domain? Zero to, okay, what goes around it? Bracket, parentheses. Yeah, that's how we would say that. But then when they talk about the increasing, notice they just put a parenthesis there. It doesn't matter whether you put parentheses or bracket on this. It does on this, but it doesn't there. Most of the time, they'll never say that. When they say the interval for increasing or decreasing or constant, they'll always put parentheses on it. So don't sweat. Do I count that or not? Don't sweat it. Just put a parenthesis. Okay. Just a minor point. Okay. Anything else about the square root function? Here's the graph of it. Okay. Intercept here, both x and y. So far, except for the constant function, every one of our parent functions crosses at 0, 0. Constant function crosses wherever c is. Okay. Now, and so far, every one of these functions has a point 1, 1 on it. Okay. The parabola does like this. The cubic function does like that. The square root function does like this. The linear function does like this. They all go through 0, 0, and 1, 1. Okay, just rather strange. But they all change in between and past, but so far they all go through that same point. Okay. Domain, only that part. Range, only that part. And this doesn't flatten out either. It keeps on climbing, just very, very slowly, but it keeps climbing. Okay. Any questions on the square root function? Okay. Now, the last of these is going to be the reciprocal function. The graph of the reciprocal function is what? Here's the reciprocal function. What's the first thing you notice about it? What smacks you in the face when you see that function? So it's a fractional form. And what? Okay, fraction has a numerator and denominator. The numerator, it will come into play later. It's just a 1. Very innocuous. What's the deal with the denominator? It's a variable, and now you have to keep that from being 0. So this has, what's its domain? As long as x is not equal to 0. That means all the negatives up to 0, but not counting 0. And all the positives from 0, but not counting 0 to positive infinity. So this is how they express it. The negative infinity, the domain is negative infinity to 0, but with a parenthesis union with parenthesis 0 to positive infinity. Only thing you leave out. That's why I like it, not equal to 0. It says it much more concisely. Okay. Now, they're giving you the range here, but what does the range really have to do with? The range is, in many ways, governed by what that numerator is. What is that numerator? I'm trying to think of the best way to ask this. The only way that function, the function itself, could be 0 is if that numerator could ever be 0. 1 can never be 0. So therefore, the range also has to exclude 0. But there's no other value that has to be excluded. Because you can put an x in here, a very small x gives you very large numbers because remember it's reciprocal. As x gets large, this gets small. As x gets small, this thing gets large. Okay? So you can get to any other number in the world, but you never can get to 0 because that numerator is not 0 and never will be 0. So therefore the range of the function is also from minus infinity up to 0, but not counting 0, and then from 0, but not counting 0 to positive infinity. Okay. Now, this may not be as easy to see. Is this function even or odd? Odd. Did you read that before? Okay. All right, good for you. Now, what happens if you put a minus x? What's the test for even or oddness? Put a minus in there. What happens if you put a minus there? You get exactly the opposite of what alpha x was. Okay? So sure enough, it's an odd function. What does that also tell you? It's symmetric about the origin. Very good. So we know that. Okay. What's this intercept? It doesn't have it. It can't be 0 on X. It can't be 0 on Y. It can't intercept either axis. Okay. Later we'll give another name for this. We say the x-axis is, the y-axis is the vertical asymptote, and the x-axis is the horizontal asymptote. Vertical asymptote, the function can never touch it or cross it. Horizontal asymptote, in general, could be touched or crossed, but that's where it's going in the long run. In this case, it never crosses it, because we've said it's not in the range. So therefore, it has no intercept from those. Now, how about increasing, decreasing? We haven't seen it yet, have we? Okay? Would y'all like to plot it before they do, or just watch theirs? Huh? Plot it, okay? I've just got to find some, here's a good white space. In fact, here's a graph. Just ignore this one. Okay. So we're going to do alpha of x equal 1 over x. Give me an x. 2, okay? So alpha of 2 is 1 over 2. So when you go to 2 here, you'll only go up here. You want me to do this in a different color? Would that be helpful? Okay, what color would you like? Get out of there. Okay. Say again? Blue. You want light blue or dark blue? Light. Okay, baby blue. Carolina blue here. Okay. So that's going to be 1/2. Or 2 1/2. Give me another x. 4. Alpha 4 would be 1 over 4. So 4 out here would be 1/4. That would be somewhere about there. Give me another x. 5. Alpha 5 would be 1/5. That's getting closer to 0, but still not there yet. Okay? We're running sort of out of high number. Give me something less than 2. Okay, alpha of 1. What would that be? 1. Okay, I can do that. Oh, there, it's on that graph, isn't it? Okay. Next. Alpha of 1/2. Okay. I'm going to work this one out. 1 over 1/2, right? What's that the same as? 2, because it's 1 divided by 1/2, right? And that is 1 times 2 over 1, which is 2. So 1/2 will be 2. Okay? Give me another one. 1/4 would be, want to make a guess on it? 4. Got it. Guess what? This is also the reciprocal function. Whatever you put in here, the output is reciprocal of it. So you put in 1/2, the output is reciprocal of 1/2 is 2. Reciprocal of 1/4 is 4. Pretty easy to do once you think of it that way. So this will be alpha of 1/4, which would be here. That's going to be 4. Okay? What do you reckon this is doing here? It's approaching the y-axis as x gets smaller, approaching the x-axis as x gets bigger. There you have it. There you have half of it. What did you not give me? Okay, and how do you get that? Negative x's. So give me a negative x. Alpha of -1, what would that be? -1. Very good. So that's down here. Okay. Another one. -2 would be -1/2. There. Oh, you don't have a 2 here, but it would be right here. Okay. Another one. Alpha of -1/2. We already did 1/2. That would be -2. That would be down here. So you see it's doing the same thing over here that it did there. Symmetric about the origin. Odd. This is going up too high here. Never reaches or crosses the x-axis nor the y-axis. There's this graph. So, now that we've graphed it, can you tell me anything about its increasing or decreasing nature? Okay. Decreasing when x is going from -infinity to 0, but not touching 0, can't be 0, but also is decreasing from 0 but not touching 0 to positive infinity. So it's decreasing everywhere of course, except at 0, it's not defined at 0. So everywhere on its domain, which excludes 0, is decreasing. Okay? But it's not, and I'm going to throw a word out to you. It's not a continuous function because down here never touches up there. There's no way. This has a big break at 0. Okay? But everywhere else is decreasing. All right, good deal. Symmetric about the origin, we said that. Okay. There's their showing of the graph. Not quite as pretty as ours, is it? But close. Okay. Don't answer that question. There's your reciprocal function. The first, except for the constant function, that didn't go through the origin. But guess what? It still went through 1, 1, didn't it? So they really like that. Okay. All right. Now, boy, there's a lot of blah, blah, blah in this section. Very few examples, just blah, blah, blah. Okay. So we'll actually go to step and piecewise defined functions. Okay? Now, we already talked about piecewise defined functions earlier. We're now going to talk about the graphs. Functions whose graphs resemble a set of stair steps is known as step functions. Okay? The most famous of these, I don't know if it's all that famous, is the greatest integer function, which is denoted by this little symbol. It, to me, looks like a double bracket. Okay? But I'm teaching from a calculus text that from their slide set, I'm going to go back to black if it's okay, or dark purple. Okay? They do greatest integer like this. So if you have no other reason to expect something else from the bracket, that could be greatest integer function. That's on the slides. But in the text for that book, I've never seen this before. They do it this way. I can't even do it. I'm sorry. So used to not doing it like this. Okay? I'd never seen anyone do this before. That's how they do it. So if you ever see that and say, what in the world is that? That could also mean greatest integer function. Now I can almost imagine that a little bit. Greatest, so they left off the top curlicue on it, you know, it's not a curlicue angle on it. So you'll see different forms for it. This book uses the double bracket. Okay, now what does that mean? F of x, here is in words, the greatest integer less than or equal to x. So give me an x. 1. What's the greatest integer less than or equal to 1? 1. 1 is, okay. You can't have 2 because that's not, I said, yeah. Greatest integer less than or equal to 1. 2 is greater than 1. You can't have that. But 1 is equal to 1. Okay, so integers are themselves. So far with integers, that would be just like the identity function. Okay, except that this does things other than integers. Give me something other than an integer as x. Give me an x. Say again? Not an integer. Okay, 2/3. What is the greatest integer less than or equal to 2/3? 2/3 is not an integer. The greatest integer. Say again? 1 is greater than 2/3. It says less than. 0! Yes, you got it. So it's the greatest integer less than or equal to x. So on the integers, it does just like the identity function. But for everything in between, it's flat. The greatest integer less than or equal to 0 is 0. Less than or equal to 1/2 is 0. 2/3 is 0. 4/5 is 0. 5/9. Yeah, 5/9 is 0. Yeah. They're all 0 until you get to 1, and then it jumps up to 1. It's solid at 1 and goes all the way over, but at 2, it jumps up to 2. So that's why it looks like a stair step, right? It's flat. It's an integer. 0, 1, 2, 3. These are integers, but they're covering the domain of all real numbers. So everything up to that integer is the previous integer, and then when you get to that integer, it goes that, and everything past that is that integer, then you get to the next integer. That's what your greatest integer function is. So, we didn't do any negatives there. You tell me, what's the greatest integer less than or equal to negative 1? Negative 1, exactly. What's the greatest integer less than or equal to negative 1/2? 0 is greater than negative 1/2. Negative 1, you've got it. So you have to step backwards there. Now, I don't know if you noticed it before. For all positive numbers, whether they're fractional forms, decimal forms, or whatever, just throw away the fraction, throw away the decimal, whatever the integer is, like 1.7, 1, 7.3, 7, 7 1/3, 7. You know, whatever it is, throw away the other part. But when you go on the lower side, you have to always look to the left. So it's the next integer to the left, which is going to be 1 less. So the greatest integer less than or equal to negative 1/2 is negative 1. Okay? Not 0. Good deal. Okay, let's do some more. Let's see. Greatest integer of 1/10. 0. Greatest integer of 1.5. 1.9. Okay, very good. All right. So here's how it looks on a graph. Greatest integer of 0 is 0 in any fraction form. Greater than 0 but less than 1 would be this. But when you get to 1, it jumps up here to 1. Because the y values are integers. Greatest integer in. The x values are all real numbers, but you can only be an integer answer. So it goes up here. When it gets to 1, it jumps up there. When it gets to 2, it jumps up there. When it gets to 3, it jumps up there. Okay. So on this end, they're open. This end, they're closed. Same thing with the negatives. Negative 0.5 will be a negative 1. Look to the left. Okay. So again, they go like that. Stair steps. That's why they call them stepwise functions. Now, boy, some mathematician went out of his way to make something rather dumb, didn't he? Okay? Do we have any stepwise functions that you ever run into in nature and in the real world? Say again? Okay, have you ever mailed a letter? Okay, did you put a stamp on it? Okay, did one stamp fit any letter you happen to mail? No, they go by weight, right? Anything less than 1 ounce is going to be the, what is it now? I only use forever stamps, I don't even know what it is, 48 cents or whatever? Okay, let's just say 48 cents. When you get to 2 ounces, it's going to get what? It jumps up to 78 or whatever. I don't know what it is. They're stepwise functions. You put it on the scale, anything less than a certain weight is going to be a certain value. Okay? And then when you go next, you jump up to another one. There's a stepwise function there. And for all the masses between 2 ounces and 3 ounces, same cost. So yeah, we run into them. Now I don't know, phones are getting so difficult, but I can remember one time the phones is you had a flat rate for up to so many minutes, and if you exceeded those minutes, it jumps up. And that was a step function, wasn't it? Yeah, you run into them all the time. Okay? So those are stepwise functions. Okay. Now some of those, you don't have a letter with 0 mass. They will send that for free. You don't have any. So that's an open circle here, and up to 1 ounce, it won't be down here, it'll be 48 cents or something. So it'll be an open circle here and a colored here. Once you go over 1 ounce, it jumps up here, open circle, dark, yeah, and it jumps up like that. So some things will have them, but they're still stepwise functions. I see motion, which unfortunately probably means, sadly, we've run out of time. We didn't quite, yeah, we did we? No, we didn't do. We'll start next time. Y'all thought you were through with this. We'll start next time with these characteristics of the step and piecewise defined functions. Homework exercises. Think you could do either 11 or 13. Any of the odds 15 to 25, try them. Okay. Any of the odds, try these two, 27 or 29. Well, do 27. We'll do the rest of them later. Okay? Stop there. Now, if you'll hang on, if you can't afford to hang on for just a minute,